All right. Cool, cool. Well, before we jump back into the homework, let me tell you one more story. So last time we started talking about potential energy, which, of course, we love energy. No, didn't mean to do that. Because energy is just numbers instead of vectors or whatever, so it makes life a whole lot easier. No, I never want to switch to a tablet, even if you tell me to. There's going to be a way to change that. And we said the potential energy is KQQ over R. Maybe with a minus sign, I can never remember, but just like forces and stuff, I think it's easier to just find the magnitude and then think about whether it should be positive or negative at the end. So, cool. So that's for if you have some fixed particular charge and then you want to find the potential for a charge that's moving around or whatever. Another one that goes along with that, it's the exact same formula. If you want to do the potential for a charge configuration, so basically the idea is you want to build some particular shape out of charges or whatever. Think, okay, how much energy does it take for me to do that? Then it's that same formula. So it's, well, U is going to be, you're going to sum over every pair of charges and then do KQ1, Q2 over R or whatever. So it's just, you do that same formula for every pair in your deal. So sure, let's do one just real quick. Let's say if we had say we wanted to put 4 charges all in a square, even though that doesn't look like a square, but pretend like they're all the same. So A and A. All right. And say all the charges are Q. Well, if I think about every pair, there's 6 pairs altogether, right? Because I could go like the 2 in the corner, those 2, those 2, those 2. So that's 4 of them. Or I could do the diagonal ones, right? So you have to do that formula for all 6 of them and add them together. Of course, since this one's a nice symmetric shape or whatever, I mean, most of them are all the same. So like the 4 side ones are all the same. So I'll have 4 of the guy that's K, Q, and the Q's are the same. So it's just Q squared over the side length. So this is from the 4 side pairs. And then I'll have 2 copies of the guy that's from the diagonal. So still KQ squared over how far apart are these 2 guys on the diagonal? If the side length is A, then what's the diagonal length? It's A times root 2, because, yeah, you go A squared plus A squared and then take the square root of it. So you get A, but then square root 2. So A square root 2. So that's how much energy it would take to put those charges together or whatever, if you wanted to. But again, since that one's just like the other, whoa. There we go. Not really going to belabor that. I mean, it's kind of the same thing. All right. Whoa. So the big thing I want to talk about today is something called the electric potential, or most of the time people just forget the word electric and just say the potential. So just like when we were doing forces, we said, well, you can think about the force between 2 charges or something, but a lot of times it's easier to just think if you have 1 charge, it makes this mysterious electric field that's kind of like a force field. But I mean, it's there whether you put another charge in it or not. we're going to do the same thing with potential energy. It's like, okay, if just like the electric field was force per unit of charge, so why are you not writing? Okay, so just like the electric field was force per unit of charge, we're going to do the same thing. We're going to say the electric potential is potential energy per unit of charge. So like for our fixed charge we had earlier, the V would be just KQ over R. So we just took out the charge of the one that's not fixed. Right. Okay. And basically everything you learned about the relationship between force and energy, it's all the same for the relationship between electric field and charge, or electric field and electric potential. So just like before, well, let me write it the calculus way, and then I'll tell you what it means for not calculus. So before we had force was, or not, I wrote that completely backwards. Before we have work was integral of force dot dr, which all that means for us, since we're not doing calculus, this is force times distance times cosine theta if the force is constant. Right? It's going to be the same thing for the electric potential. So the electric potential, since it's just W over charge, and since the force is just, well, the electric field is just the force over charge, then you're going to have the same thing. So electric potential is going to be the integral of E dot ER, which, again, for us, is just going to mean this is E times however far you go times cosine of theta. If the electric field is constant. Okay, so let's just do one simple one and then we'll jump back to the homework. So let's go with our parallel plates because that's the only constant electric field we know. So so E is constant, which we said it was actually sigma over epsilon naught. Right. So let's say this is the positive, this is the negative. So if I go out distance, I don't know, let's say D for distance. So the electric field is pointing sideways. I'm moving out sideways. So the cosine theta part, they're in the same direction. So the angle is 0, so the cosine is just 1. So anyway, that just means the electric field is going to be E times D. Or if you want to write it as like we did up before, it's sigma D over epsilon naught. But yeah, basically it's just, it's whatever the electric field is and then times however far out you go. So, cool. All right. And, okay, let me say one more thing. The last thing, the reason potential energy was really, really useful to us before is because it tells us about work, right? I mean, we had work was the initial potential minus the final potential. This is back in physics 1. And we love this back in physics 1, right? Well, the same thing's going to be true. I mean, we don't really care about, well, ultimately what we want is still work. but it's going to be the initial potential minus the final potential. Oops, final potential, and then times Q, right? Because remember, all this little electric potential thing it's just the actual potential energy per unit of charge. So if I multiply by Q, I'm going to just wind up with potential energy again. All right. And this leads us to our last word, which is this thing right here is called potential difference. Which, when we get to circuits, I mean, basically that's what makes circuits run. So it's like you have a battery is just some sort of mechanism for creating two spots of different potential right by each other. So you hook up to one, hook up to the other. Well, yeah, electrons are going to want to move from one to the other. Okay. Well, let's go back and see what's in the homework.